Hello, this is going to be topic number 8, Flexure, part 2, and in part 2 of this video, we're going to cover 8.3, the beam equation, and 8.4, dealing with FlexPDE flexure. So, the beam equation. We've looked so far at the fact that moments lead to curvature through flexural rigidity and figured out how to calculate all of these things and how this bends a beam into a constant circular arc as long as m over EI is actually constant, which it will be in a pure bending situation of a beam with a constant cross-section along its length. It's okay if the cross-section changes, is not like a uniform cross-section. Like maybe it has a stiffer material at the top than the bottom, like that bimetallic strip we looked at, but it has to have the same cross-section on different parts along the length of the beam for that method to work. But in general, the moment and flexural rigidity aren't constant, so it would be helpful to learn about how local curvature, which is still modeled by this, leads to an overall beam displacement in general. This is going to allow us to solve statics problems that we weren't able to solve before, like how much force shows up at each end in response to an arbitrary applied loading function if you have a double fixed support setup. So this is going to first derive the beam equation, which is a way to determine the overall displacement from curvature caused by non-uniform moments as long as the displacement stays small enough, which is typically true. So the first thing we need is this relationship here. For small deformation bending, it's going to turn out that the beam cross-sections stay approximately in the YZ plane, right? If we're not moving too much, then the thing that was originally the YZ plane is still in the YZ plane. And the curvature, this is referring to beams which are long in X and are subjected to moments in Z. That's when this would be the YZ plane, the like X surface, the positive X surface that we're looking at as our cross-section. Then the curvature is going to be approximately the second derivative of the Y displacement per step in X. This is going to end up being the curvature. To see this, we can have a look at an equation of a circle. So let's suppose that we've got a circle that's centered at 0r. So it's displaced up by its radius, and this means that the bottom of the circle is going to be at the origin. Let's have a plot at a circle like this. So to do this, we're going to use implicit plot. And the syntax for that is to give the equation that we're trying to plot directly, which is x squared plus y minus r all squared equals r squared. And we'll say some r. Let's imagine just r is 1, but we could scale this later if we like. Then we need to also give a range on x equals negative r to r, and a range on y0 to 2r. That's going to be a good range for this one. Okay, so there we go. There's our circle. And right around the bottom here, what we're saying is that the curvature is basically the curvature of this circle, which is 1 over the radius of curvature that we're getting, 1 over the radius of curvature at any point on this beam, is approximately the second derivative of y with respect to x. So let's have a look at that. For the equation of the circle, what is the second derivative of y with respect to x? Well, first things first, the equation of the circle is basically the same as the equation that we get if we ignore this y squared term. So with the y minus r squared factored through, the r squareds cancel, and we have a negative x squared over here is equal to y squared minus 2 times y times r. If we drop the y squared term, then we'll have the equation of a parabola. And this is basically what the circle looks like as long as we're staying close to that origin. We're not letting the y get very large. Let's have a look at that parabola. So it's equivalent to this y is x squared over 2r. Let's plot that too. Y equals x squared over 2 times r. And yeah, sure enough, this parabola lines up with the circle as long as we're close to the origin. We can change the scale here and just plot up to maybe r over 2 and have a look at this. So you can see the circle really does match up quite well with that parabola when we're close. Do you know which one the circle is? The circle is actually this one that's farther in on this size scale. I know it doesn't look much like a circle with this skewing of the axes, but the circle, if we go back to the larger size scale, is the one that goes above and leaves the parabola early. So to say that the displacement from a given curvature, like if we have fixed curvature, that's saying that the displacement would be kind of parabolic. That is going to underestimate the actual deformation that we would have, because it's going to, really the thing would go up and back and around, right? Whereas if we have a uniform curvature beam, it's going to bend into the arc of a circle and go up and back on itself. And that's not what a parabola would do. The parabola is just going to keep going more and more up and never accounting for this x displacement and bending back. But at least as long as we have a small displacement, then we can say that this is a reasonable approximation to what's going on. It's going to turn out to also be true at any point locally, as long as v is really the transverse displacement, right? So it always works around the edge of the circle pretty well if you don't take too big of a step. So if you just recalculate what your transverse direction is at each spot, then this equation will work more broadly too. Okay, so again, the parabola that we got is y is c, x is x squared over 2r, and c is 1 over r, right? Curvature that we have is 1 over the radius. So the second derivative of y, the y coordinate of this, which would be the displacement if the beam has bent into an arc of a circle, would be equal to the second derivative that we get of c times x squared over 2. Take one derivative, and you're going to have c times 2x over 2, which is c times x. Take another derivative, and you've got c. So the second derivative of this parabola is just c, and that's why, at least locally, this second derivative of y position per step in x is called the curvature. It ends up telling you what the arc of the circle that this function is bending in is. So now that we know how curvature is related to the transverse displacement caused by the bending that produced that curvature, we can solve for the curvature that we would get by solving for a bending moment that shows up internally, and then use some and then take some integrals in order to figure out what the actual displacement is. So let's take a particular case. Let's take a beam here which has a distributed load on the top, which is P naught at each this is like per unit length like we were dealing with before. So its total length is L, and the total load that's put on it is negative P naught times L in the down direction. So that means that these supports have to each put half of that up as reaction forces. So we have L times P naught over 2 applied upwards. Then, using the previous sign convention that we had, we can figure out what the internal shear force is. So there has to be an internal shear force that counteracts that upward RA, and then gets reduced by the amount that P naught has acted on this as we go along the beam. So in the center, we should have a shear force of 0, and then right before the end, we'll have an internal shear force that's negative this direction because it has to hold up most of the beam and do exactly what RB is doing. So here's the shear force internally from that logic, same stuff we were doing before. And the internal bending moment, there's no bending moment applied at each of the ends, so we can work out by doing this manually for each step over x that we'd have RA times x, and then we'd have this negative P naught x kind of equivalently applied at half of the displacement, so multiplied by an x over 2. You can see that the RA would tend to reduce the internal bending moment in this direction, in the positive z direction, say, if this is x to the right and y up. And the P naught applied to that little piece would tend to reduce how strong the internal bending moment needs to be. So here's the bending moment, or as usual, we could have just integrated the shear force and we would have gotten the same thing. You can check that this thing here is also the integral of this thing. So the 1/2 showing up because we integrate x, and we get the x squared over 2. All right, so now that we've found out what the moment is, we can use the new information that we have. That moment is EI times the curvature, and the curvature is the second derivative of displacement in the x direction, to find out what the displacement is at each point along this length by integrating. So we know m, it's this thing, and we can figure out EI using the stuff we did in the first part of this lecture video, and that is the one that was in the previous video, but the first part of the Lecture 8 notes videos. Yes, the first video on the Lecture 8 notes. And then once we've got M here and that EI, we can integrate twice in order to find V. But like any differential equation, we're going to need conditions. So in this case, it's boundary conditions. We know that V at the start here is going to be equal to 0, and we know that V at the end is going to be equal to 0, and that'll do. That'll tell us what the displacements need to be at all different points along this thing for this to work. All right, so let's go talk through how to do this. In the notes, I've gone and shown you the analytical version of doing these integrals, but let's do this with Maple here in the video, just for a little bit of a change and a different view of the same content. Okay, so we've got a force at each end, which is P0 times L over 2. So we'll say we can figure out where that came from by first solving that RA plus RB minus the integral of P0 from x is 0 to L is one equation, and then maybe torque about point A, sure, RB times L minus the integral of x times P0, x is 0 to L, should tell us that RA and RB both have to be equal to L times P0 over 2. Now here, because we put L as a variable and P0 as a variable, it found two different solutions here. One of them actually is finding the RA and the RB, but the other one is saying, we don't know what those are. We could be that L is 0. Yeah, that'll do it. That's kind of a trivial solution here. What you can do if you want to do symbolic solving is just also tell the solve command which variables you'd like it to find, RA and RB. So here we go. We've got RA is that, and RB is that. So what we can do is assign the op of that, and now we should have RA and RB assigned. Yes. Okay, now we can find out what the shear force is internally by saying that the shear force is going to have to counteract this force at RA, and then deal with however much distributed load we have so far. So we'll integrate the distributed load, x is 0 to whatever x spot we're kind of taking this split at. And this should give us the shear force all along the way. Yep, same thing that we found there. And we can also integrate that to find the bending moment. Bending moment is equal to the integral of V, x is 0 to x. We don't have any pure point moments applied, so it's just that straight integral formula of V, and this does produce the same, or at least should produce the same bending moment that we just calculated, does it? It has half P0 L times x for the first term, half P0 L was RA, and then we've got this half P0 x squared for the second term. Okay, as a check, when x is 0, this gives us 0, and when x is L, it also gives us 0, because then the first term is going to be the same as the second term. Now, the moment divided by EI is supposed to be equal to the curvature. So first, let's figure out what EI is for this beam. Oh, you know what? I guess we don't know anything about the beam's cross-section in this example, so let's just leave it as EI. So we'll say C is equal to M over EI. Fair enough. So there's that. All right, great. Now, the displacement has to be the integral of this twice. So we'll say V is equal to the integral of C with respect to x. When we do that, we're going to get two arbitrary constants, or at least we should. But the problem is that this integration right here doesn't know what to add for those constants. So let's say that first v prime is equal to the integral of c from x is 0 to x, and this is v prime here. Problem is, this thing has no slope at point 0, but point 0 is a pin, and maybe there is a slope there, right? So we'd better say v prime is equal to this plus v prime 0. You know, whatever the slope was at 0 will be will now be telling us what we'll put in there. This is a parameter we're going to have to solve for, and then we'll be able to say what the slope is everywhere else along this beam. Now that we have this, we can then say what v is by, again, integrating v prime from x is 0 to x. So let's try that. And again, this did a definite integral because that's how we wrote it out there. We've got now multiplying v prime by x, but again, we need to multiply the start by, or not multiply, we need to add the start to the start, v0. We need to add the initial constant that we would have had when v is equal to 0 to the start of this. So this is really finally the final position at each step along the length. So we see here, we had a v prime at 0 that we were left with, and we've got our v0. So let's just check. We've got that the slope, or rather the displacement at each point is the initial displacement plus the initial slope times x plus 1 over EI times L P naught over 12 times x cubed and minus P naught x to the 4 over 24 EI. Yeah. So now we can apply some conditions. What we know is that the displacement at 0 has to be equal to 0. And we know that the displacement at the end has to be that same displacement. So let's just do that. We can solve that subs x equals 0. First of all, does subs work? What do we get when we say subs x equals 0 into v? Okay, it works. We get our v naught there. What about subs x equals L into v? Does this work? So we get our L to the 4. Let's see. This is L to the 4 as well, but only over 12, and that's why we're left with over 24, and then VP0L. Okay, looks like the subs commands works. So let's say solve that the subs of x equals L into v is equal to 0, and subs x equals 0 into v is equal to 0 as well. When we solve this, we should also, again, tell subs which ones we're looking for. So let's say we want to solve it for v naught and vp naught. And we should get that v naught is equal to 0. You can sort of see that that would be the requirement for this term right here when you sub in a 0 to get a 0 for that. But it's less obvious what vp0 should be to make this 0 at the right-hand side as well. Let's see. So we have v naught equals 0 as promised, but v prime at 0, the other parameter, then needs to be negative p naught over 24 times L cubed over EI. All right, so if we do that, if we substitute those things in, then for whatever values we have for L, EI, and P naught, we will have the curvature of this thing. So what do you think this would look like? What do you think, sorry, not the curvature, we'll have, the curvature we could get as well from V by taking the second derivative. We do still have the curvature, but we also have exactly what the displacement is, this new thing here. So what do you think this should look like? Well, if it's pinned there and pinned there, it should kind of bow down, right? Sort of look like that, like an upward sloping, maybe parabolic looking thing. It actually looks like it's a quartile function with a negative term here and a positive term for the cube and a negative term for the linear function. So let's see what this looks like by assuming some values for EI. Let's just take EI is equal to 1, P naught is equal to 1, and is that all we need to assign? L. L is also equal to 1. Why not? And now we'll plot V from x is 0 to L. Let's see. Okay, so looks kind of parabolic, right? So V is actually equal to this. It's in fact a quartile function, but it starts off with a position of 0, ends with a position of 0, and has this slope, this kind of downward arc, and then back up. If we have EI is 1 and this is 1, then it slopes down by 12 millimeters at most, a little more than 12 millimeters in the middle of this 1 meter length. So using this, we could also plot what the moment is, or plot what the curvature is that's going to be proportional to the moment. And the moment is not constant for this case. We've got the maximum moment at the middle where the shear force is 0, because the shear force starts off at a maximum and then decreases down to 0 and starts increasing starts decreasing further to become more negative in the other direction. And the shear force is the derivative of the bending moment. So that explains why the bending moment being the integral of the shear force looks kind of like this and reaches a maximum at the middle. That's when the curvature is a maximum. So we get close to these we get basically to like a linear function at the end with no curvature when the moment goes to 0 there. But then when the moment is a maximum, we have the most kind of arcing of this beam. Well, that was fun. We used a lot of stuff, and we basically just said, hey, we've got this M is related to the curvature through flexural rigidity, and we know how to calculate that if we need to. And from this relationship of how curvature depends on displacement of the beam, and knowing what the displacement has to be at the start and end, we were now able to figure out something we never were able to calculate before, which is the deformation of this beam. We previously knew how to find those shear force and bending moment diagrams for something like this, but what we didn't know is how the beam would actually move in response to that. And that's kind of cool. Now, what in there of all these equations was actually the beam equation, right? We had this titled the beam equation. Actually, it's none of this stuff. Well, so what is the beam equation? Let's talk about it. Another way we could have done this thing was to just start from the moment is EI times curvature relationship, and then take a derivative of that and have an expression for shear force in terms of the third derivative of V, and then take a derivative of that and say that the derivative of the shear force is the distributed load, which is just EI times now the fourth derivative of V. This is the beam equation. So this thing here, this fourth order differential equation, is a way that we could just solve directly for the deformation without having to know other stuff about what's going on. Like, we applied all this static stuff to figure out what the shear force had to be and the bending moment by applying these torque equations. The net force is 0 and the net torque is equal to 0. And then we used an internal shear force and bending moment diagram to figure out what the shear force has to be and then relate that to the bending moment by integrating. And then we use the relationship that relates curvature to bending moment in order to and integrate 2 more times this bending moment that we found, applying some initial conditions, well, really boundary conditions, on V at the start and end of this beam in order to figure out what V was for this thing. But another thing we could have done is just said, hey, you know, we've got a fourth order differential equation here. We know EI, presumably. We know P naught, presumably. So and we know some conditions on V at the start and the end. So we ought to be able to derive all of these things just directly, right? Let's see if we can do that. So we'll start again, forget everything we know about V, M, all that stuff. And down here, we're just going to say EI is equal to 1 and P naught is equal to 1 and L is equal to 1. Then what we're going to do is ask for a desolve of what? Do you remember how desolve worked? It's been a while. So here's a practice problem from week 1 where we were desolving a differential equation and initial conditions. And the differential equation, we put in something like this, and then say the initial conditions by saying what x at 0 was and d of x at 0 as well. And then we'd be able to solve for what the value of x is, x at t in this case. So back to topic 8, what we can do is say desolve of the beam equation, negative P naught is equal to EI times the fourth derivative of V with respect to x, which we can write by diff of v at x with respect to x, 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 and then x, fourth order differential equation. And we're going to solve this subject to the initial conditions, or in general, really boundary conditions. So let's see, what would the conditions be? We've got that v at 0 is equal to 0, and v at L is equal to 0, yes. But what are the other conditions? We never had to apply these in the previous way that we solved them, so they must have been applied somehow implicitly with the way that we solved these equations here. In fact, they are. So the other equations have to do with the joints. Because we've got a pivot joint at each end, if you think about it, a pivot joint tells you something about some derivatives of v. Not about v itself. Well, it tells you that v is 0, but it doesn't tell you anything about the angle of v, which is the first derivative of it. But it does tell you that we can't be applying a moment at that end. So the second derivative of v has to be 0 if it's a pivot joint, right? So this means d, syntax for multiple derivatives in dsolve showing up here in one of the other questions from the first week. D, we'll use square brackets 1, 1 to say with respect to its first variable. So the third derivative, d, 1, 1, 1 of v evaluated at 0 is equal to 0. And the third derivative of v evaluated at L is also 0. This comes from the need to have no bending moment at either end of the pin joints. So the bending moment tells you something about, oh, not third derivative, the second derivative of this function. Yeah. Second derivative of what v has to be. All right. So let's see what we get. Look familiar? We also found the displacement without ever having to solve the statics problem. So now that we've got this displacement, okay, that's fantastic. We could go and plot it just like we did before, but also we could do some different things. We could figure out what the angle that the beam is making at each point is by taking the derivative of it. So we could say theta is equal to diff of v with respect to x. Okay, that's fine. Oh, wait a minute. We didn't assign it. Right. So from the end of this dsolve thing, I remember making this mistake back in week 1. You guys remember that? So now v, after we've done that, we have to say v is equal to the right-hand side of the previous thing. Great. Now that we've got v actually assigned to this, we can take the derivative of it to find theta. And here's something fun. The second derivative of it times ei should be m. Diff of v with respect to x twice. And then v should be equal to the derivative of that. All right. So now we've got our internal bending moment and shear force. Without ever having to have solved the statics problem explicitly. So previously, we learned that a shear force should be giving this thing a shear stress. We've got a lot of shear force on this thing, and that should give us a shear stress. And we learn how that's related to strain via this equation. The shear strain should be equal to the change in vertical displacement per change in horizontal step. But we just found out what the displacement was, and we didn't include this anywhere. In fact, we didn't even give it a Poisson's ratio, so there's no way that we figured out what g was somewhere hidden in this. And the reason that we didn't do that is because we just ignored it. And we ignored it because it's probably ignorable. The setup like this, if we have a long beam compared to its thickness, then likely bending is going to dominate even in a situation where you don't apply a pure bending moment like we did in the first part of this set of notes, but in a situation like this where you have all of the bending showing up from shear. We still have bending. We didn't put it in that pure shear stuff we were dealing with last week, but even though we don't have pure bending, the bending is going to dominate due to the geometry of the beam. We can compare this actually by working out what the shear deformation should be. So let's take the same example that we have here, and we'll get things a little bit more explicit. Rather than this EI equals 1, let's go with E is equal to 1 megapascal, and let's suppose that the B is equal to 1 centimeter, and the H is equal to 1 millimeter. 1 millimeter and 1 meter in length is extremely small. Maybe let's go with H is 1 centimeter, maybe B is 5 centimeters and H is 1 centimeter. Okay, so then with this Young's modulus, we're going to have an EI, which is equal to E times B times H cubed over 12. So the EI is this small amount. It's a lot lower than 1 in this setup. Maybe let's make it bigger then. Let's go with a gigapascal of material for this. Actually, you know what? Let's go with 250 megapascals, and now we've got pretty much an E of 1, just like we had before. All right, why not? So now we can figure out what the cross-sectional area is for this beam, now that we've specified what B and H are. And with this known, we can go and figure out what the displacement would be from shear by calculating the shear stress. Tau on X in the Y is equal to V, big V. Now that we've got V, so I guess we'll go at the end here. Tau on X in the Y is V over A. And then the shear modulus we could have found out at the beginning. G is E over 2 times 1 plus nu. And we'll then get a slope of shear displacement, V shear, V shear prime maybe, is equal to tau over G. And then V shear is equal to the integral of V shear prime from X is 0 to X. All right, let's see. Oh, what did we forget? Oh, tau xy. That's what we called it here. You could see that that wasn't defined there in the end. So, oh, the nu seems like it's not known as well. Did we forget to put that in? Oh yeah, we need a Poisson's ratio. So let's say that we've got a typical Poisson's ratio of maybe 0.3. And then V shear is 0.00001. That's 1e minus 5 times x squared, and another 1e minus 5 times x. So we can plot it alongside the displacement that we had previously. Let's suppress this. No, we'll hold on to this plot. Why not? So we'll get a new plot though. Plot, not just V, but also this new V shear from X is 0 to L. Okay. A little bit hard to tell what's going on there. We've got a, so here's the displacement from bending. We have this much displacement, yeah. What about the displacement from shear? I'm not sure where it is. So let's maybe add the displacement from shear. We'll take the original bending, and then the displacement from shear will say, yeah, we'll account for that shear displacement too, and see how that affects things, and add them together. Okay, great. Yeah, I don't see anything. Let's zoom in. We'll go X is maybe L over 2 to some small amount difference, some small different amount, L times 1.01 over 2. Ah, there we are. We're at the bottom of this curve, and we can see that adding in the shear deformation has corrected the displacement by only a very small amount. So the bending displacement alone tells us that we should be at negative, for this beam, 1 meter long. We've got a 1 Newton per meter force applied on it as a distributed load. It's 1 meter long, 5 centimeters wide and 1 centimeter thick, made of a material with a Young's modulus 250 megapascals, and the bending deformation that shows up on this 1 meter by 1 centimeter thick thing is about 0.01 in size. But the shear deformation is on the order of 0.000 something, right? So we've got 0.000, this is 5, and then minus 0.0003. Wow. 0.00003. Oh, I didn't have enough decimals in there. 0.000003. Is that right? Let's check. What is V? Let's just plot V shear by itself. Yeah, so V shear ends up with values on the order of 1e minus 6. So the bending displacement has given us a deformation of 1 centimeter, and the shear deformation on this thing alone is a correction on the order of 2 microns. So the bending is around, it is around what, 5,000 times more displacement than the shear deformation? Yeah. Now that is going to depend on the dimensions of this beam. So let's see if we can systematize this. We'll find out maximize abs of V over, for x is 0 to L, and then we'll compare that to maximizing the absolute value of V shear from x is 0 to L. So for the current dimensions, the maximum value of bending is around 5,000 times as much as the maximum value of shear, and that's what we calculated by looking at the numbers there too. What if we change the dimensions? So I want to see the output of this, so let's, yeah, okay, we're okay. Let's go with not 1 centimeter thick, but how about 10 centimeters thick? Now, shear is not 5,000 times weaker, it's only 50 times weaker than bending. What about 1 meter thick? Now, shear is actually more important for the displacement than bending is. Shear is twice as strong as, or shear is responsible for twice as much of the bending displacement as, or twice as much of the displacement, the vertical displacement, as bending is when the beam is the same thickness as it is in length. The reason for this is that shear ends up being proportional to the length of the beam divided by the cross-sectional area, whereas bending ends up being proportional to the length squared over area times h squared, which means that it's compared to the shear displacement like a proportionality difference of length over h squared times the shear displacement. So the as the aspect ratio of the beam, as the length to thickness ratio increases, bending becomes more important than shear according to L over H all squared. So if you have a beam where the length and the thickness are about the same, you're going to need to account for the shear displacement. If you have a beam where the length to thickness is on the order of a factor of 10, then the shear is going to be on the order of 1/100th as important as bending. And it just becomes more negligible if you have even higher aspect ratios. Okay, so summary. The internal shear force and bending moment are related through this equation that we had earlier. For appropriate sign convention, we have to set the V to be in the right direction compared to the bending moment to get that to work. Let's put that here. And what else? The moment causes a curvature in the beam via the flexural rigidity. So the moment is leading to a curvature via flexural rigidity here. If the curvature caused by the moment is all of the strain, and the strain is reasonably small, then the curvature is equal to the second derivative of the deformation caused by bending. This, therefore, ignores the deformation caused by shear, which would be related to, which would be coming from the shear strain related to shear stress, according to this equation. And although it looks like we're simultaneously saying that V is equal to something proportional to the third derivative of displacement, shear is equal to the third derivative, and shear is equal to the first derivative, this first one is based on only the displacement caused by flexure, but the second one is based on only the displacement caused by shear. The true displacement you'd really have to get by considering both of these effects together. All right, let's do an example with cantilever boundary conditions. Suppose we have a 1 meter long beam that is 10 centimeters thick and 20 centimeters wide. Yeah, I guess this one is not quite 20 centimeters wide. We're just showing part of the width. It's got a longer thickness than it has width. And we're gonna deal with this and see what we have. So again, not quite to scale. Figure out if E is equal to 100 gigapascals, nu is 0.2, what the deformation is in the y direction versus position relative to the wall. Okay, so we can again set everything up like we just did. So we'll say that we have a distributed load, which is equal to 1e3 per meter. We've got a length, which is 1. We've got a thickness, which is 0.1. And we've got a width, which is 0.2. And what else we've got? We've got a Young's modulus, which is 100 gigapascals, and Poisson's ratio of 0.2. So Young's modulus of 109, and nu is 0.2. Okay. So next up, we can put in the beam equation. And the beam equation says that, well, why can't we just use the beam equation and solve it? Because we know what the distributed load is. We don't have any other point loads applied along this length. So this is going to be valid for a differential equation solving along the whole length of the beam. So beam equation says that P naught is directed downward. So we'll say negative P naught is equal to, what was this again? It's derived and written right there. Starting off with m is equal to EI times the second derivative of V. You take two more derivatives of that to come up with the derivative of the shear force has to be negative P naught, which is EI times the fourth derivative of V with respect to X. So negative P naught is EI times diff of V at X with respect to X 4 times. And then we've got some initial conditions. So this particular beam is fixed at the left and free on the right. And that means that at the left-hand side, with a fixed support, we don't know what the shear force is. It could be anything. We don't know what the moment is. It could be anything. But we do know that the angle of the beam is 0 and the displacement of the beam is 0. So that means we can say d of V at 0 is 0 and V at 0 is 0. Meanwhile, at the right-hand end, which is a free end, we don't know what the angle or the displacement is, but we do know that there's no applied moment and no applied shear force. So that gives us that the second derivative of V at L has to be 0, and the third derivative of V at L is equal to 0 as well. All right, so that should let us solve for V. Well, at least in terms of EI. I suppose we should also put in what EI is. EI is going to be equal to E times B times H cubed over 12. We could do the integrals across the cross-section. This is just what it ends up being for a rectangular region with constant parameter values. So we can jump right to this if we don't have the parameters changing. Okay, so with that in mind, we have what the displacement is, and we could give something a decimal point value, maybe 100.0E9. Oh, that doesn't do it. What's going to force this to evaluate? Maybe P naught 1.0 E3. Well, I guess we could just say V is equal to eval of right-hand side of mod. Yeah. So anyway, here's our V calculated, and we've got what the displacement is. So that's what they wanted, right? Find the deformation in the y direction versus position relative to the wall. We've got it. We could plot that as well. What do you think the cantilever is going to do with this load? It's probably just going to slope down somewhat. So let's see. V from x is equal to 0 to L. Yeah. Did we need to care about the shear deformation? We could say what G is. E over 2 times 1 plus nu. And then tau x in the y is equal to V over A. And we're going to need to compute both of those. So what is V? First of all, M is equal to EI times diff of V with respect to x twice, and V, big V, shear force, is equal to diff of, whoops, I've opened PowerPoint. It's the wrong hotkey. Not right now. Diff of V, or maybe we could say diff of M with respect to x again. So then we'll say that the shear force is V divided by A. Technically, this is the shear force on x in the negative y, I guess I should say. And so I suppose that is a mistake that showed up in our last problem that we did there. So the shear force really should have been negative V over A. And I guess this is a problem. We didn't really think about what direction the shear force was. The shear force is making it move down more because we have a positive shear force directed downwards, and that would mean a downward displacement. That makes more sense. So that's why it is actually lower than the bending moment in that previous example. Okay, so tau on x in the y is negative V because V was directed downwards over A. And then we can figure out what V shear is by taking this tau xy and dividing it by G, and then integrating this from x is 0 to x. All right. The other thing we need is the area, and we could figure that out by putting in area is equal to B times H. Okay, so there's the shear deformation, and we can plot that as well. Plot V shear, x is 0 to L. So from shear alone, we end up with displacement that's on the order of something E minus 7, which is not much compared to the E minus 5 that we got from the bending alone. We could plot them both. Plot V plus V shear, x is 0 to L. And it's not going to be that different from just the bending plot by itself. You'd be hard-pressed to notice a difference because this is only a 1 part in every 100 correction to the bending deformation. Also, notice that the shear deformation is becoming less and less prominent as we move along because the shear force goes to 0, but at that point, we already have so much angle built up that the bending deformation keeps adding stuff even though there's no more bending moment. So this approach that we did, we could compare with the approach where we directly find the moment and the shear force and then integrate a couple of times rather than using the beam equation. So let's try it. We can put in all of the stuff that we had at the start from last time. And from statics, we can solve that Ry minus the integral of P naught from x is 0 to L has to be 0. And the torque equation will now say the net torque in the outward direction. Oh, why are the coordinates in this thing so messed up? That's weird. We were saying x was the length direction, wasn't it? Yeah, x is the length direction. Y is vertical. Z is out of the page. Huh, that's a weird picture I chose for that, eh? Okay, it's fixed now. It can't hurt us anymore. So X is to the right, Y is up, and Z is out of the page. And now we can use this to write out what the net torque is. So we have on the full thing, not just the internal shear force and bending moment diagram, that's why we're taking this all the way to L, we have that RM is going to be out of the page in positive Z. We have no torque produced by Ry here, but we have a torque produced by the distributed load, which is going to be in the opposite direction to Rm. So minus the integral of X times P naught from X is 0 to L. So this should let us figure out what Ry and Rm are. Okay, so let's see, we had a kilonewton per meter and a 1 meter length, so that makes sense that we have Ry as 1,000 and that Rm is 500 Newton meters for Rm and newtons for Ry. So we'll assign that. And now we're in a position to write out what the internal shear force is. So the shear force would be Ry minus the integral of P naught from X is 0 to X. And then we could figure out what M is by saying that it's the integral of V from X is 0 to X, except that M is going to have to also consider what Rm is. So we're going to subtract off Rm when we consider that thing. So let's have a plot then of what V and M are and compare that to what we found using the beam equation. So here we didn't actually write out what V and, well, we found them, I suppose, but we didn't actually plot them. Let's plot that now. Plot V and M from X is 0 to L, and we get, that looks familiar. Same shape, down to negative 400 and up to 1,000 in different units for shear and for shear force and bending moment. But yeah, so down to 500 actually. We know that that's 500 where it hits on the end and goes gradually up to 0. Shear force starts at 1,000 and decays down to 0. Nothing applied on the right. Maximum of these applied at the fixed support on the left. Okay, so that agrees. Then the statics thing we got definitely agrees with the beam equation approach. Beam equation not so great if you just want the shear force and bending moment diagram compared to our earlier methods for finding that. But it is more convenient for finding out what the position is and the bending moment is. Still, as long as we can find this shear force and bending moment, we can now go and find out what the curvature is by saying curvature is equal to M over EI, and then find V by integrating the curvature twice. So this time, when we integrate the curvature, really we'll get V prime by integrating it once. Integrating the curvature, X is 0 to X. This will not add a constant if it behaves like the last time, and that means that we have something which is 0 at the wall, and this time, that's perfect because we had a fixed support, so we need no slope at the wall. So now we just integrate this again. Integral of V prime, X is 0 to X, and we should also be adding no constant from the way the definite integral is working, and we'll end up with the displacement. So let's see, did we output that down here for this other version? Looks oh wait, it's just ordered differently. So we've got the same term there for the x to the 4, and 1e minus 4 times x cubed, yep, and 1.5e minus 4 in the negative 4x squared. All right, so we have the same displacement function solved using our old statics methods and to find the moment and then integrate that after we divide it by EI and turn it into curvature to find out the displacement, or the beam equation method, which has us not actually solve the statics problem, just write out the differential equation, the beam equation, and apply the boundary conditions and determine directly what the displacement is from that. So to solve this problem, we have two different methods. Our old statics method to find out the internal bending moment and shear force, and then convert that into displacements using the new elasticity methods for each of those we have last week and this week, or this new method using the beam equation, which has us not solve the statics problem, but directly solve this fourth order differential equation. Another thing that's great about this beam equation method is it lets us solve problems that we could never solve with that statics stuff from before. So have a look at this problem. We've got bridge boundary conditions. Remember in statics how we would say, all right, well, this is all well and good. It's going to hold still if we have a fixed support here and a fixed support here. But there are too many unknowns, because we could have situations where we're holding it more with the right support than with the left one. And we don't know how it's going to be deforming. And I was telling you that this is not something which is unsolvable. It's just unsolvable right now until we build in the elasticity at some point in the future. We build in the elasticity relations to the knowledge that we have. Well, the future is now, my friends, because with the dynamic beam equation, not the dynamic, that's force of habit from the future. Later, we're going to deal with the dynamic beam equation. Now, with the beam equation, non-dynamic, the static beam equation, we can apply some boundary conditions at the other end, right? So it's the same as dealing with the thing above for the cantilever, except that rather than the moment being 0, meaning that the second derivative of v has to be 0 at the end, we'll just have that v is 0 at the right-hand side. And rather than the shear force being 0 at the right-hand side because it's free, we'll say that the first derivative of v at the right-hand side, the slope, is 0 at the right-hand side because it's fixed. So the same boundary conditions at v is 0 as we have at x is 0 as we have when x is equal to L. Yes. So there's our new set of boundary conditions. That's all we actually have to change about this problem to get it to solve the same thing, but for a bridge instead of a cantilever. Right. So fixed rather than fixed free, and here is the setup. So with this fixed thing, we've got a moment which looks like this, starts at some value and then goes up 0 at some point, a maximum there, and then back down to 0 there. Shear force starts there and goes and ends up over there. It ends up still being kind of symmetric in terms of how much force is supported on each end. And there we go. So if we wanted to know what the reaction force is, you could just figure out what the shear force internally is right at the wall, and that has to be counteracting the wall's reaction force. So this shows you it is indeed the most balanced approach. It's got 500 there, and then 500 on the right end as well, and actually a fair bit less than half the moment, because we don't need to apply nearly as much moment at the walls in order to counteract these things, this stuff, when we have a force at the other side. So you might have thought there isn't going to be a moment at the wall, but it turns out when you build in the elasticity stuff, there needs to be to counteract the way that the thing is deforming. So what we have here is a requirement, not just like a pin support where you'd have the force and the force there and it would kind of slope down. It's not allowed to have that angle, so we have to force it to hold up by applying a moment at the wall. And it's negative the internal bending moment that we had with our sine convention applied at the wall. So this would be one that on the other side is applied up opposite of RM there. So that means we're putting a moment in the direction that RM is showing there to stop it from bending, from sloping down. We're kind of pushing it out at the bottom of the wall to stop it from going into a pin support. Imagine what it would do if it was a pin, and then think about what moment you'd have to apply to stop it from sagging down and doing that pin displacement where it's able to have that angle. So now let's build up how to do this in FlexPDE and check these results that we were doing in Maple. Now I know what you're thinking, this is already a pretty heavy week analytically for what we're doing in Maple, so Dr. Minnick, I just can't handle if FlexPDE is too complicated for this week. And the good news is we don't actually have to modify the FlexPDE program we developed before at all. The only thing that we need to do is apply different boundary conditions for whatever thing we want to solve. So let's take this past thing here, this bridge boundary condition problem, which had the parameters set up here, and then set it up. Let's make it long in X by 1 meter. We're going to make it 10 centimeters thick in Y and 20 centimeters wide in Z. Then I guess we can give it a new name, topic 8, example EG 8411 video. And let's see then, what else do we need? We need to know what the applied stress is on the top. And this is going to be something that would produce 1 kilonewton per meter when it's applied over 1 meter of length. So that's kind of convenient. We just need to take a force of 1e3 and divide that by Lx and Lz. That's the top surface, right? So that's exactly what we do in order to figure out what the stress applied to the top surface is. We need, in FlexPDE, a force per unit area. You need the direct stress that you're applying to that surface, and that's what we're going to apply. Okay, now the Young's modulus is 100 gigapascals. So let's see here. E is 100 E9. Poisson's ratio was 0.2. And then all we're going to have to mess with is the boundary conditions. So we're already drawing a rectangular prism here. We have it fixed at x equals 0. And now we'll just have it fixed at x equals L. And this should be doing nothing. This should just hold totally still. Let's check. All right, looks good. That's the geometry of the beam, and it looks like this one, but this is rotated sort of strangely, right? The Z is up and Y is out and X is along this length. So actually Y is in into the page where we're showing it here. So this is the origin 0, 0, 0 down there. Y is increasing in that direction, the direction in. So yeah, let's apply the stress though. How do we apply this load on the top surface? We're going to need a load in the negative Y direction on the Y equals Ly surface, this top surface here, the one that we got. First we start off at 0, 0, 0 here, and then we draw a line over to Lx0, not changing the boundary conditions for that line, meaning we have no load along the bottom. Then we go up to Lx, Ly, but before we do that, we say everything's fixed. Nothing can move on this new surface there. Then we go from that corner to 0 Ly, going back, and on that surface, we've said that there's no load, except we're going to say that the load in the Y direction is negative S applied. Now we say it's fixed from there to close, which is going to be the x equals 0 surface. So this really draws lines, and what makes them surfaces is after you do all of that stuff, we say, let's extrude it from Z equals 0 to Z equals Lz, and it keeps all of the boundary conditions on each edge that we applied here in 2 dimensions when you extrude it into that 3rd dimension there. You can also apply boundary conditions on all of the Z equals 0 and Z equals L. I guess Z is increasing in this direction for the diagram. Yeah, by putting them in here. But we're just going to leave those surfaces free at load equals 0 by specifying nothing. All right, so let's see how that goes. Yeah, we've got some bridge deformation there, as expected. And so the shape looks right. Let's compare that with the numbers we got in Maple. So here in Maple, we've got our V value, and we can determine what it is in the middle by substituting x equals L over 2 into V. And V mid is negative 1.56 microns. Let's see what we get in FlexPDE. So we can say summary of V in, sure, let's plot it in the middle. So at half Lx, at Ly over 2 and half Lz. How about directly in the middle? And then just in case it depends on where we are at in X or Y, let's make a contour plot of that. Contour of V on X equals Lx over 2 painted. So here we go. The displacement looks like it changes around at different spots on that surface. This is versus Y, the thickness dimension here, and Z, the width dimension. It looks like it's around 1.7 E minus 6, whereas here in Maple, we found it was 1.56 E minus 6. So not exactly the same. Not exactly the same in each of these. Let's explore why it might be different. One of the things in Maple that we didn't do here is include the shear deformation. So now that we figured out what V shear is, maybe we can see if the shear would be giving us extra agreement. Well, the shear is so small, it's on the order of, let's see, shear is around 1 E minus 7 here. And, yeah, so that is around the difference between these two. Let's add the shear deformation to the bending deformation and see what we get. V mid 2 is equal to V mid plus, or how about just subs X equals L over 2 to V plus V shear. Okay, and that does give you around 1.7 times 10 to the negative 5. Does this actually work at each end? So what about if we plot V shear all the way along this thing? Plot V shear X equals 0 to L. I think we might have already been doing that. Yeah, so it does go back up to 0 at the other end. So it looks like if we include the shear deformation in Maple, then we end up with a lot closer to the deformation that FlexPDE is giving us by including all of the deformations, not just the bending, but also the shear. So now that we've got this FlexPDE deformation, we can explore what was going on in these edges to stop it from having that pin support set up there. So on this edge, what we have is a bending moment that's applied to stop it from bending into that pin shape. So let's see, that means probably if we were to look at the stress in the X direction on X equals 0, we'll see a highly compressive load at the bottom of this at, where's the bottom? In Y, at Y equals 0, right? So this is kind of a strange rotation from what's going on in this picture. So at Y equals 0, at the low Y value, we've got a high compressive axial stress in X, and at the high Y values, we've got a high tensile axial stress in X. So what that means is the X direction is pushing out on the bottom here and pulling in on the top to stop it from just kind of bending and forming like a pin support there. By the way, we can kind of apply a bit of a pin support by saying on this X equals 0 surface that instead of the value of U is equal to 0, we've got a load of U equals 0. What this does is it stops the thing from being able to push with moments on that edge, right? Because the X stresses are mostly what's required to have these moments. And now it bends into this kind of pin support and then up fixed support on the right. The displacement exaggeration that we're using here is making the thing look kind of a strange shape and get a little bit size change there on the edge. But this is basically showing you the right idea. From this point being a totally fixed support and this point being a pin support, we now can figure out what the displacement is at certain points. So one other thing we can do is compare the displacement we get at halfway with this to the displacement we would have calculated if we set it to a pin support on the left in Maple and compare this. So this is no longer the point of peak displacement. The peak displacement occurs a little bit to the left of the middle there. Let's see what it is in Maple. So how do we change the left end to a pin support? Rather than saying that the slope is 0 at the left end, we'll say the moment is 0 at the left end. So that would be this. And I think that's all we actually have to do to change it to a pin support at the left-hand side. Now we're saying in the middle, we've got a displacement of about 3.2 e minus 5, which again agrees pretty well, 0.32 e minus 5, so 3.2 e minus 6, which agrees pretty well with what we got in FlexPDE by changing the left-hand side to a pin support as well. Now, if you look closely, you can see the limits of this analytical approach in Maple by noticing that the shear is predicting that we don't actually go back to a 0 displacement at the other end from shear alone, but it definitely should be doing that from the shear alone displacement. And if you're going to sum these in superposition, we should be ending up at the same spot as before. But we don't. So this is a bit of an error in this current approach. We are only able to apply one boundary condition in shear because it's just a first order differential equation by itself. So really, we should be building up this differential equation to account for shear and bending together from the start, rather than just doing this fourth order one in bending displacement alone and then adding the shear displacement later. But we're just going to deal with this as a limit of the current more approximate approach of figuring out what scale the shear deformation should be about and what scale the bending deformation should be if it's the only thing that is there. And sometimes it's going to be valid to add those by superposition and get what we and get something closer to what's going on in FlexPDE. But really what we should be doing is solving the total differential equation for both of those things together, or doing an approach that doesn't rely on the small deformation approximation, and that is what brings us to finite element methods to begin with. So since Flex is able to solve a more accurate representation of the statics problem here, we might want to extend the amount of different problems we can solve in Flex by figuring out how to apply a pure moment on an end of a beam. This is something that we aren't able to do right now. We did this by applying a load in the vertical direction on the top of the beam rather than actually applying a bending moment at one end. So we can't actually put the beam into pure bending and solve those things from the first part of lecture notes from this week, until we figure out how to apply a pure bending moment in FlexPDE. So to investigate this, let's consider in general what happens when you apply an x-directed stress over an x surface. The net force that's produced, we know, is the integral of that stress over that surface, but we also have torques produced about different axes based on the displacement away from that axis times those stresses. So let's take this one where the origin is there. So the axis parallel to z would be y equals 0, or I guess actually this y equals ly is also parallel to z. But let's say about this one, about the y equals 0 axis, we're going to have a torque in the z direction if we find the torque produced about this axis by these stresses. And you see these ones are making it, are kind of rotating it around that. So that's going to be producing a torque in the negative z based on how strong they are and how far over they are in positive y going to the right here. Yeah, so the torque in the z direction about the line y equals 0 would be negative the y displacement from y equals 0 times sigma x with respect to area integrated over the surface. If you wanted instead the torque in the y direction about z equals 0, which is this line, so the torque about like the bottom line there, you would base that on how far up the points are. And now the right-hand rule tells you that up crossed with these stresses coming out will produce a torque in positive y based on how far up the point is above z equals 0. With this in mind, not any stress distribution will necessarily produce a pure moment. If the stress distribution has any net force at all, then it's not producing a pure moment. And if the stress distribution produces a different torque about different values of, about different points you could find the torque, so we wouldn't be subtracting z equals 0 here, but z equals something else, then it would not be a pure moment either. So let's solve this one item at a time. A way to convert a stress distribution, sigma, into one that produces a pure moment is to subtract off the average stress over that surface, because now when you find the net force produced by this, you're going to find the net force produced by this one, which is sigma x times the area, and then you're going to be subtracting off this thing integrated over the surface, which is just going to be this times the area because this is a constant. So this one here, sigma x prime, which is any arbitrary stress minus its average over that surface, is going to be producing no net force in the x direction. So that's one step. What about the torque? So this is kind of a necessary condition for producing a moment. The other thing we need for it to be producing a moment is that it produces the same torque about any parallel axis. So this thing turns out to produce the same torque about any parallel axis. Let's see how we would see that. The torque that it produces about y equals 0 would be the displacement away. So y equals 0 is an axis parallel to z. It's the negative displacement in y that you are away from that axis times sigma x prime. And sigma x prime is just sigma x minus sigma x bar. And the displacement that the torque that it produces about the right-hand side would be the y coordinate minus Ly, which is going to work out to be a negative number and give us a positive torque, as you'd expect. And when you substitute this in, you need that these two things are the same for this to be producing a pure moment. It produces no force because of that, the condition that we subtracted off the average stress already. But does it produce the same torque about these two parallel axes? It does, as long as the extra term that we have in this integral is always 0. And it is. Why? Because this Ly displacement of the axis is a constant, so you can factor it out of the integral. And now we've got inside the integral of sigma x minus sigma x bar. But that's 0 for the exact same reason that the net force produced by this thing is equal to 0. So this means that any stress distribution which produces no net force must therefore also, if it produces anything at all, produce a pure moment. Let's think about that another way. If this produces a net force somewhere, so if you can replace all of this with an equivalent force, then depending on where you look, that force will produce a different torque. So it's not producing a moment by itself, right? But if you break the stress distribution into a part that produces a pure force like this, the average stress that's constant over the whole thing, and another part which has no average stress because you've subtracted it off, then this part has no net force. So it's just made up of stress couples, right? Stress pairs of forces in equal and opposite directions, and those produce pure moments. So another way to put this is that the net force produced in the x direction by an x stress on an x surface is the integral of that stress over that surface, and we can define that as the average stress times the area. Then the moment that same stress will produce about the z-axis, so the moment in the z direction, I should say, same as about the z-axis. Moment in the z direction is negative y minus y naught times sigma minus this sigma bar, sigma x bar. And the moment in the y direction is positive z minus z naught times sigma minus sigma x bar. Now what z naught and y naught do you use? It doesn't matter because these are pure moments. So no matter what point you find the torque about, you should get the same answer. So this tells us for any stress distribution, not only what the force that it produces is, but what the net moments that are produced by it would be. So you can replace this stress distribution with an equivalent x directed force and moments in y and z. So let's explore this. Find a stress distribution that creates a pure moment mz on a rectangular cross section from y equals 0 to ly, z equals 0 to lz. So the center of this cross section is ly over 2 and lz over 2. And we want to be producing a moment mz on this cross section. So let's see how we could do this. We can take a sample stress, Sx, and work out what moment it produces. So for any given stress, let's say that we make something with a y dependence. We'll say that Sx is equal to Sx naught times y over Ly. Why not? And then we'll find out the force that's produced by this. Fx would be equal to the integral of Sx from y is 0 to Ly, and z is 0 to Lz. So let's not suppress that and just look at what that output would be. It's kind of like it is just integrating the thing over the surface, but because you have a y dependence, we end up with like a y squared over 2 thing, but we canceled out the other Ly by scaling it here. So this scales up from 0 to Sx naught as we go across the surface. So the net force produced is the area times Sx naught over 2, which is the average value there. So we can say that Sx bar is equal to the average value of the stress, which would be Fx divided by Ax. And what's Ax? Ax is equal to Ly times Lz. This is the same as our previous area formula, where we're kind of saying Sx bar would be this integral of the stress divided by the product of those lengths, just the integral of 1 from y is 0 to Ly and z is 0 to Lz. So there's our Sx bar. Now we can say Sx prime, which is not the derivative or anything, it's the offset one, is equal to Sx minus Sx bar. And the assertion is that this thing should produce no net force and should produce a pure moment if it produces anything at all. So let's find out. Fx prime would be equal to the integral of Sx prime from y is 0 to Ly and z is 0 to Lz. And this should be 0. And it is. So our analytical work was successful there, at least so far. What about the moment? Mz that's produced will be negative the integral of y minus something, y naught, times Sx prime from y is 0 to Ly and z is 0 to Lz. Doesn't even matter what y naught is. Let's simplify this thing. No, Ly or y naught is gone. It cancels out in this setup, and we have a moment produced, which is negative Sx naught Ly squared Lz over 12. So we have the same moment produced regardless of whether this stress itself, whether we were taking the torque that it is producing about 0 or about any arbitrary y naught, it didn't matter. The y naught cancels, so that shows indeed that this torque is producing this stress is producing the same torque about every point, so it's producing a pure moment on that surface. Okay then, what we're often interested in doing is rewriting this to get some expression for what the stress would need to be that produces the moment that we're looking for. So we could solve, maybe we'll get rid of this thing. We'll say that the moment is equal to simplify of this. And then what we'll do is we'll say that Sx naught is equal to solve that thing for Sx naught. Right. So that is the stress that we're going to apply for whatever moment we're looking for this to be the stress function. And then once we've done that, we have our actual stress function is this in terms of whatever moment we're looking for. So that means that we just need to apply this thing for whatever moment we're looking for, and we've got it. As a check, we can again find out what the moment that is actually produced by this stress is by simplifying negative the integral of y times sxp. Y is 0 to ly, and z is 0 to lz. But because of how we defined this, this is just going to work out all simply as the moment. So the moment that's produced by this stress on the surface is whatever applied moment we're looking for. So that's all well and good. If we have something which is scaling from 0 to ly and 0 to lz, this formula will always be working out for us to produce whatever moment we're looking for. So we just make a function which is 6 times mz over this thing and negative 12 times mz times y over that thing. Maybe we can simplify it a little bit. What about factor this thing? Will that help us out? Yeah, that looks pretty nice. Go maple. So negative 6mz times 2y minus ly over ly cubed lz. So that formula might seem nice and convenient, but it is not so great if we have a non-uniform cross-section, right? We've got a cross-section that is not a rectangle. What if we have a cross-section that goes from y is 0 to 2 and z has a thickness, the width, z is 0.5 from y is 0 to 0.2 and 2 from 2 to 0.5, and z really the width is 1 from 0.5 to 1. How do we find a complicated z width function? Really, I should say like the width in z. Width in z is this, and this is really not z, but like let's say the width w there, and z width function. Yeah. So let's repeat it's really the process of the above that is going to help us out with this. So rather than this answer per se, let's go back up and try out this same process again. So we've got some stress. Yeah, why not this thing? Sure, looks good. And now the area is not just this. We're going to have to integrate. We can replace all of these integrals with multiplying by a width function like we did earlier. So w is piecewise of, I know the maple code is on the screen, but I'm trying to ignore that. W is equal to a piecewise function. If y is less than 0.2, then we've got 0.5. If y is less than 0.5, we don't have to say greater than 0.2 because if we're even checking this condition, we already know that it's not less than 0.2. W is equal to 2. And if y is less than 1, then w, let's just even say greater than 0.5, then w is equal to 1. Okay. Oh, we didn't incorporate that. We forgot to say what that means. So now we're going to integrate, we're going to take sx times w from y is that, and sx bar will be this over ax. I guess we can find out what ax is. Ax will be the integral of w from y is 0 to Wait a minute. 2? Okay, what is this on the rest of the range? No, y is 0 to 1. Yeah, that makes sense. That's what we actually solved here. So we'll take y from 0 to 1. And yeah, let's just take this as sx naught y over 1. What function do we use to give the correct moment? Oh my goodness. What happened there? We said sx naught, and then we put in our w. Let's do this one thing at a time. We've got w, and then we don't know what fx is. Oh my goodness, we forgot to say what ly was. So we're going to take all of these integrals and go 0 to 1. And then this next integral, fx prime, will be w times sx p, this new thing. Oh, this is just so much. Let's kind of comment out stuff and check that code works and do this one thing at a time. So yeah, we don't know what sx naught is yet, but the fx is equal to this times whatever sx naught is. And then we subtract off the average value, which is fx divided by the area, and we end up with this thing here. Yeah. And now we have something which should produce no net force. Let's check that. And it is sometimes 10 to the negative 10, so that's basically 0, and should produce the same moment about every point. So the y naught should drop off after we do this integral. So we'll do w times that, and we'll take the integral up to 1, and then close the bracket for the simplify function. And the y naught term disappears. Okay, perfect. So next, we will deliberately get rid of y naught just so we don't have any kind of numeric error in there. And we'll say that sx naught is determined by what we would get if we solved the previous thing for sx naught. So sx naught is now written in terms of some moment. And now we can write what sx prime is in terms of that moment. Factoring it doesn't really do that much. And maybe check it. So let's integrate over the whole surface now. Width times y, from y is 0 to 1. And we get, indeed, the moment back. So this process that we've done a couple times now is all right. It's an okay process. You start off by defining any stress that has some y dependence. We chose a linear one. We could have chosen some quadratic one or anything with a y dependence. And then we figure out what the force that it produces is and the average of that stress. You subtract off its average stress, and now you've got something which produces a pure moment. And all you need to do is find out the moment that it produces and then scale the constant that we used for stress to make this function produce exactly the pure moment that you wanted. So that process we've done a couple of times, and that's all nice, but can we find a closed form solution for this stress? Yes, we can. And it turns out that this is one. As long as we work with the average y position, the non-E weighted centroid, just the regular centroid. So how do we come up with this? First, we just do the same formulation by starting with this function. So this says we're going to start with a sigma naught y minus y bar over Ly. And it turns out that this thing produces no net force, and we can prove this analytically based on the definition of what y bar is. So the net force that's produced by this, we would have an integral of our y minus y bar over Ly term. This is the stress we're asserting will have a form of a pure moment. Now, we can take out the sigma naught and Ly, and we're left with just this. But this integral of y with respect to the area will be the same as if we just took the average y and multiplied it by area. And that's exactly what we had for this other term integrated over the area. So we get 0. So this stress function here without the dA, this thing produces no net force, and that means it's in the right shape to be able to produce a pure moment. So what moment does it produce about Z? Well, the moment that it produces about Z is, as usual, the integral of sigma x times any offset y, so y minus 0, for example, with respect to area. And this is going to be the same as y minus y bar. So we may as well just subtract off y bar if we like. And then we can calculate this moment, which is going to be an integral of sigma naught over Ly times y minus y bar all squared. And that lets us now write out what sigma naught needs to be to produce this moment in Z that we wanted. So that's it. The stress function that we're looking for would be what we get when we sub this sigma naught in times y minus y bar over Ly. And the sigma naught subbed in then makes the Ly actually cancel, and we get that a stress distribution of the moment in the Z direction that we're looking for, that produces the moment in the Z direction that we're looking for on the X surface, would be equal to that moment times y minus y bar over the integral of y minus y bar all squared with respect to area. So let's calculate that. We can check it for this exact version that we just did. So let's take maybe sigma x is equal to negative mz times y minus y bar. Let's figure out y bar. Y bar would be equal to the average y value over that surface. So it's going to be the integral of y times the width from y is 0 to 1, in this case, over the integral of the width from y is 0 to 1. That's going to give us y bar. Okay. And let's see, y bar ended up being close to the middle because we've got 2 for this thing from 0.3 to 0.5 and 0.5 at the end of it, and then 1 on the top. So I guess we've got about the same area below as above. Y is 0.5. Okay. So sigma x is not just this, it's this divided by the integral of y minus y bar all squared with respect to area. So we multiply by the width and then integrate from y is 0 to 1. So this is purported to be a function now. Notice that we integrated the y in the denominator, so this is not proportional to y, but we didn't integrate that y in the numerator, so this is still a function of y. And we've got a function which should produce the pure moment that we're looking for, and it looks as if it actually is the same function that we just calculated up here. Let's see. Well, that didn't make things much simpler. Let's try evolve instead. Expand. Okay, there we go. That's the one. So it is actually the same function as we had earlier. So we've got this 0.495 times the 13 gives us a 6.52, and now we did this closed form way of finding out the function which will produce the pure moment that we're looking for just by writing out what y bar is and then writing out this new function in terms of it. Now that we know this, could we have spent the last 20 minutes by just writing this down and I would say, hey, here's the stress that happens to produce a pure moment. Don't believe me? Check. Yeah, we could have done that. But I think that this is actually useful to see as an example of how you can generate equations for stuff or just solve problems using math in general, right? So what we did is we just started off with really not a lot known, and kind of worked out the equations by writing down what we did know. So we said, all right, let's find the net force of this stress distribution, and if it's going to produce a moment, it has to produce no net force, so let's just subtract off the part that's producing a net force, and hey, we've got something with no net force. Does this happen to produce the same torque about every point? Let's figure out how to write those torques, and sure enough, it does. So this is producing a pure moment, and the moment is this about each of the different axes that we're looking for. Then we went in and made up any function and saw if we could, first of all, maybe just explore that the calculations we were doing before worked, that it does, after we subtract off the average stress, produce what we thought it should, which is no force but a pure moment. And then we scaled it to make it produce the moment that we wanted. And after we got used to this with some special cases, we were in better position to come up with a more clever way of writing a function and checking that it really does do what we're looking for. Where's the inspiration for this? Well, this is going to be something that produces no net force because it kind of scales to be centered around the center Y in the area to begin with, which is where the logic for that was. And it's linear and scalable, so we can figure out what sigma naught has to be to produce exactly the right stress. So this last method is applicable to a lot more than just finding out the stress function that happens to produce the moment that we wanted. And I think that this procedure, if you followed along and enjoyed it and can see where that would be useful in other situations, is a lot bigger of a problem-solving technique than the information that just comes from this magic formula here. So finally, now that we've got this stress formula for how to produce a pure bending moment, let's see if we can apply that and compare with the work with the displacement we would have gotten analytically using the work we figured out earlier. So suppose we have a beam that has dimensions 4 and 0.5 and 1, made of a material with E is 5 gigapascals and nu is 0.2, placed into pure bending by fixing the x equals 0 surface and putting a moment of 10 kilonewton meters on its x equals Lx surface. Find the expected curvature and tip displacement and verify it using FlexPDE. So this is going to be a bit of a review from the earlier part of this week's stuff. Let's see. So we've got a moment of 10 E3, and we've got a length of 4. Ly is 0.5. Lz is 1 in meters, so kind of a wide beam here, quite large dimensions. And the material is E is equal to 5E9, and nu is, what do we say, 0.2? 0.2. And we're going to place it in pure bending. So let's see. We're going to figure out EI. EI is equal to the E times, we could integrate, well, we could even do it once. Integral of Lz times y minus y bar squared from y is 0 to Ly. But Lz is, Lz is a constant. We've got the same width all the way through it, and it's and it has the same E everywhere as well inside. So this is just going to give us E times Ly cubed times Lz over 12. The second one, we need to figure out what big Y bar is first. Y bar is equal to the average integral of E times Y, y is 0 to Ly, times Z, times Lz here. Really integral over the whole area, but we're putting that in because it's a constant. We've kind of done the area integral in 2 different steps before, just like when we had that width in there, and divide this by the same thing, but without the y, to get our weighted average. So here's our y bar and our EI, and it's the same as if you use this one for the rectangular cross section in case you have that one memorized. Thickness cubed times width divided by 12. All right, so there's our flexural rigidity and the more general way to calculate flexural rigidity as well. Now that we've got that, we can go in and figure out what the curvature is by saying that the curvature that shows up, we need this to figure out tip displacement. Curvature is equal to the moment divided by EI. And let's look at the direction here. We got a positive moment in Z. And so this curvature is going to be telling us what V is by integrating C twice. Okay. So we're going to find the integral of C from x is 0. Oh, wait a minute. Hold on a second here. Let's go x is 0 to x first, and x is 0 to Lx. Does that actually make a difference? Let's see. It does. Why is that? Because this one would be finding out what the angle would be at the end. And if you assume it has like the end angle all the way along when you're finding out the displacement, you're going to get a larger value than if you say the angle it should have at any point and then add up those little steps to find the final value. So like this will give us the displacement at any point from equilibrium, and then we can find V tip by saying subs x equals Lx into V. People make this mistake every year. They just do these things as definite integrals, and it will not give you the right answer for the displacement at each point or the tip displacement at the end. Okay, so this is what we calculate using Maple for the expected tip displacement. What about in FlexPDE? Let's take our code and we'll save it as a new thing. Pure bending. Yeah. And this is, I guess, example 8423. And what do we need? We have Lx is 4, Ly is 0.5, Lz is 1. The E is 5 gigapascals, nu is still 0.2. What else do we have? We have the stress applied. We'll figure out what that is in a moment. First, let's figure out where we're going to put that. So we're going to put x equals Lx with a stress applied in U. So we'll say load of U is the applied stress, and we'll put no other loads on that surface. Then we'll reset the load in U to 0 along the top surface. So the line from LXLY, this top right corner, back to 0 LY. And then on the back surface here, we'll fix it in X as well to make sure that it definitely does apply that pure bending moment to hold it, to put it into pure bending there. Okay. We should then get something pretty close. It won't be exactly the same because we're going to be fixing it from being able to deform in Y and Z on that surface, and it's going to want to do that through the Poisson's ratio. So this is going to be restricting it a little bit and perhaps leading to slightly less displacement than we otherwise would have calculated at the tip. If we were not applying that. Got to spell applied correctly. And now the next thing to do is to figure out what that applied stress needs to be by using the result that we just calculated here, for example. So did we type that in? Yeah, we worked this out. So now we can go in this example here, work out what Y bar is. The width is just Lz. And the moment that we want to apply is figured out at the beginning. So I believe we should have it. So let's see, sigma x, according to this, should be negative 120,000 y plus 60,000. So let's take our FlexPDE code and apply that as the applied stress on this surface. So it's on a positive x surface, so we need to apply positive that stress to that surface in the x direction, and it'll apply as tensile. If we were putting it on the x equals 0 surface, because the outward normal is in the negative x direction, we need to put negative s applied on that surface to get it to work. But on positive x, we can just put s applied, and it should be all good to go. Okay, so let's take this thing we calculated. You can just copy paste from Maple into FlexPDE, and that should work out for you. Yeah, so here we go. Let's try this. We've got some bending. Looks like some pure bending there. Yep, so it's not, you can take this and sort of drag it around and redraw the shape. It is not doing a lot of shear type displacement, and the displacement at the tip is a fair bit different actually. So it's 1.9 times 10 to the negative 4 compared to this 1.5 times 10 to the negative 3. So let's debug and see what could be causing this. So it's not clear right at the start whether we have something incorrect in Maple or in Flex. So this moment that we're applying, we said y goes 0 to 1 in there. Is that still the bound? No, it's not actually. This is should really have been ly there, and same thing for this. So this is ly, ly. We were not careful enough when we copied that formula over to get the correct new y bar, and we didn't think about it. The y bar should be right in the middle. It should be 0.25, not a half. Okay, so that changes the sigma that we're applying to this surface by quite a lot. Let's see. We'll just put this in there. How different is that? Instead of, wow, that's a way different sigma. So we've got a much stronger y dependence rather than 120,000, we've got 960,000. And rather than 60,000 offset, we've got 230,000 offset. Okay, let's see. And now, aha, well, I guess that was the extent of the thing that was leading to a discrepancy between these two. The fact that FlexPDE now agrees with Maple means it's less likely that we made any big mistake there. But let's explore a little bit more from what we can tell about this in FlexPDE. One thing is what the stress is on this far surface. So we have almost a uniform stress that's changing as we move the x position on x equals, not the x position, the y position on x equals 0. Because we're bending about the z, we need to have a stress that depends on y on this surface showing up to echo what we are actually applying on the other surface. We can plot that too. We're applying that stress. So let's do, contour SX on x equals Lx, and look at the one that we're setting. So this is a perfect, beautiful rainbow of applied stress on this end surface in a pure moment. And this one is the reaction rainbow. This one is showing up in response to us putting this on the other end of it. And it's not quite as perfect, right? This is kind of, one, we're sort of propagating numeric error across the thing. Flex is always going to imperfectly solve the real problem that we have. Another thing is we have these extra boundary conditions coupling through Poisson's ratio, and that is going to make things a little bit funky there too. Can we fix that a little bit? Well, let's see. What happens if we don't actually fix, let's say, Z? So we'll put load in W is equal to 0 on that surface. Well, it gets a little bit better, right? It looks a little bit closer to this one. The scale is not exactly the same. It's close, minus 2.4 to plus 2.4. Looks like we have spots where it's higher from the little bit of fluctuations on this surface. We can also try to set no load in the y direction and see what happens. Load y is equal to 0. And now it looks even better. It looks very close to this thing. And going from 2.4 to 2.4 exactly, so we've got a real great reproduction of this rainbow on the other surface. However, the displacement is now kind of meaningless because we don't have a reference point where it's set to 0 displacement anymore. So although this is going to be a better way to calculate what the real stress is that's going to show up on that surface if we put it in pure bending, and now the beam is really in pure bending, we haven't held it still anywhere. So it's, yes, in pure bending, but it's kind of moved around somewhere that that we haven't determined. It's not fixed in position. It has no net force on it, yes, but it doesn't have necessarily no velocity. So it may have moved a little bit compared to where we were hoping for. So this is no longer the total displacement at that end. We can do a little bit better. We can try this minus the displacement at 0 and see what we get. And now it brings it back to the displacement that we were expecting. And you see, without the Poisson's ratio interfering, we actually have almost exactly what we were getting in Maple. All right, one more example, and this is a big one. This is going to be bigger than the test example that we're going to do in another video. So this is going to be a lot of fun. Okay, combined beam in Maple and Flex. We've got a beam which is tungsten and aluminum, and the aluminum has a different width and different thickness than the tungsten part. We have a pure moment applied at the end of it of 10 kilonewton meters in a direction that tends to bend this thing down. It's a cantilever. It's fixed at this side. And just for fun, we're going to call this side Z equals 0 and say that Y is up. So we're looking at like a moment in the negative X direction. Wait a minute. In the positive, hold on a sec. If it's going to bend down, we've got a moment like that, which is in the positive X direction, right? Positive X direction moment that's going to cause it to bend down on that surface. Then we have a distributed load too, which is due to the weight of this thing, which is also causing it to bend down. So fixed on the left, we've got a weight and a moment applied at the end that's going to make it kind of bend down. And we want to find out a shear force and bending moment diagram in the length direction, so versus Z, a tip displacement analytically using Maple, and the tip displacement using FlexPDE as well. Now we're going to put the origin in the center, and the first thing we're going to do is go and define the material parameters. So we'll use piecewise functions to specify all of these, and they're just going to depend on what the L value is. So E is equal to piecewise. If Y is less than 0, then it's going to be the values for tungsten, which is 411 gigapascals, 411E9. Y is greater than 0, we'll get aluminum, 70 E9. Nu is piecewise. Y is less than 0.28. And if Y is greater than 0, we'll have 0.35 for the Poisson's ratio. And the density, piecewise, if Y is less than 0, 19,250, and Y is greater than 0, converting it to kilograms per cubic meter, 2,700. As you might remember from part 1 of this two-part, massively long lecture video. Okay, so E, Nu, and Rho are as listed there, and we can write out the width as well. The width, if Y is less than 0, is going to be the width of that tungsten layer, which is 20 centimeters, so 0.2. If Y is greater than 0, then the width is the aluminum layer, which is 0.6. And Y doesn't go from 0 to Ly. Y goes from negative 60 centimeters to positive 20 centimeters. So how can we do that in a systematic way? Maybe we'll say y bottom is equal to negative 0.6 and y top is equal to positive 0.2. And then we'll just have to remember that it's always yb to yt when we're doing those integrals. Okay, so now what do we want to do? We want to get our shear force and bending moment diagram. Well, we can start this off by drawing a free body diagram, and I've got one prepared here. So this has x into the page, z that way, and y up, and we're going to have our reaction moment applied and a reaction force in y applied. We got a moment applied at the end, which we can write down as well using what was in the problem. And the bending moment at the end is 10 E3, and the we need to figure out what the weight is along this thing with the distributed load. Let's call that mu, or I don't know, maybe P naught, just to keep it what it was earlier. This would be equal to the integral of the width times the density from y equals yb to yt. Why is this? This is an integral over the cross-sectional area, right? We're integrating all the y values multiplied by the width and the density. Density is in kilograms per cubic meter, so integrating across the area will give us this kilograms per meter. Now that's not actually the force. To get the force, we would now have to also multiply this thing by 9.81. So we'll take 9.81 times that, and that will be the weight. Whoops, what did I forget here? A bracket. Okay, so this is the distributed load per meter of this thing. We've got 26 kilonewtons of weight. So that's kind of a lot. This is sort of a lot of tungsten and aluminum, but mostly tungsten. I mean, it's just as much aluminum, but the tungsten is a lot more massive than the aluminum. Let's see, we've got 20 by 60 by 1, which is, what's the volume? 0.2 times 0.6 is 0.12 cubic meters. And so we're going to have 2,000 roughly kilograms of tungsten by itself, and then some aluminum as well. And the 2,000 kilograms, when we multiply it by 10 newtons per kilogram, will give us 20,000 newtons as the weight of the tungsten. So that seems right. All right, yeah, tungsten's heavy. So at least this much of it is. So this is the distributed load that we have along the top, and we've got our moment at the end. So now we can set up our statics equations. So we can say, solve that, so let's see, net force, Ry, minus the integral of P naught from Z is 0 to L. Put in L as well. L is 1. Was 1, wasn't it? 1 meter long, yes. Okay, so L is 0, Z is 0 to L, and that's the net force in the y direction. Net moment, net torque, I should say, in the positive x direction into the page there will be mn. We'll do the net torque about this axis in the clockwise direction then. So we'll be subtracting Rm, and we'll be subtracting the integral of P naught times x, times Z rather, force of habit, from Z is 0 to L. All right, and this should be an equation that we can solve for M end and Ry because it's a cantilever, so we don't need to do the beam equation to figure out what the reaction moment and reaction force is. And now that we've got those, we can work out what the internal shear force and bending moment are. So V in that direction, V now in the pointing in negative y, as before. V is equal to then Ry minus the integral of P naught from Z is 0 to Z. And M is going to be, M is, let's see. Oh, we could do this a couple of ways. You could do the method where we consider how far away Ry is and the effect of this distributed load. But as before, the easiest way is to say that M is going to be negative Rm plus the integral of V from Z is 0 to Z. So that should give us the internal bending moment and internal shear force. And let's have a plot of those to see if they make sense. So we'll plot V and M from Z is 0 to L. Let's have a look. So it looks like the moment starts off at non-zero at the so the moment that we're applying here, because the reactionary moment was actually negative 3,000, the moment starts off at positive 3,000 and then kind of rises because the shear force is positive, but the shear force goes down to 0 as we go to the end. There's no shear force applied at the end, no externally applied shear force, no externally applied normal force either, but no externally applied shear force. And that means that we have to have no internal shear force at the end of the beam, and that means the moment stops changing there and should end up at exactly the right value to jump down from this applied moment at the end, which was 10e3, but that doesn't quite look right. You know, it looks like we've ended up at about 15e3. So something seems amiss here by what we calculated for the internal bending moment. Aha, I found something. So this torque equation is wrong. The equation that we put here, we made a sign error. This, or at least I did, I'm not sure if you did, but the moment that we applied at the end here is positive because we said in the positive x direction is this, and that's the same way that the weight is making it move this time. So we should have a positive integral of this thing added there. So because we had that inconsistency, it was leading us to something that was not quite right. Now at the end, we have, let's just double check that this is going in the right direction. After we've applied M end, it is going to be increasing the moment that we would be applying. So this would mean it would jump back up, and that makes sense for this plot of the moment ending up a little bit below at about 10,000 in the negative direction. So there we go. Now we're good for the internal bending moment and the internal shear force on this thing. Next thing that we need is the flexural rigidity, and we need that because we want to later say that the curvature is this moment over EI, and then say that the displacement is equal to the integral of the curvature from Z equals 0 to Z, and then the integral of that from Z is 0 to Z. So that's going to be the displacement. And then finally, once we've got that, we want to look at it to make sure that it is actually 0 and has 0 slope at the end, which is right for this fixed support. We can figure out what the displacement would be at the tip. Now, because this is a cantilever, it's going to be likely mostly the bending displacement that is responsible for this, because it's 1 meter long, and I don't know, actually it is pretty high. Maybe the shear deformation is going to be pretty consistent, so we might have to figure out what that is as well. So to find out the shear, how are we going to do that? We're going to say that the shear stress, tau on Z in the Y, is equal to negative V divided by the cross-sectional area, AZ. So we'll need to figure out what AZ is, right? So AZ, we'll work that out. And then once we've got this thing, we'll also figure out the shear modulus, and we'll get that the shear strain is this thing divided by the shear modulus, and the shear strain should be the derivative of the shear displacement with respect to z. So we'll say that V shear is equal to the integral of tau zy divided by g, that would be the shear strain, from z is 0 to z. Okay, so what do we need? We have to figure out the shear modulus. That one's not so bad. It's E over 2 times 1 plus nu, and we put in nu up at the top. All right. Right, now actually, this is going to be sort of complicated because the nu is not a constant across this thing. So really, we're going to have to figure out an average value of these things over the cross-sectional area and deal with that. So let's say G average is going to be an integral of W times this thing that we would have gotten to find G. Actually, you know what? Let's just keep it simple. Let's say G is equal to this, and then G average will be equal to the integral of W times G from Y is Y bottom to Y top over the integral of W from Y equals Y bottom to Y top. Now this integral that we have in the bottom, this is just the area, right? So maybe we can first work that out and then just divide by that area to make things a little bit simpler for a lot of these calculations. So this should be the average G, and then we can take this divided by G average to work out that thing. Now, EI, how do we do this? EI is equal to the integral W times Y minus Y bar all squared times E. And we're going to take Y equals Y bottom to Y top. We don't divide by anything this time because we're not calculating an average when we calculate flexural rigidity. But in order to do that, we do need the average Y position. And this one, is an average, W times Y. And we're going to weight this with the stiffness, Y equals Y bottom to Y top, over the integral of W times E from Y equals Y bottom to Y top. Okay, so here's our Y bar that we're going to use to calculate the flexural rigidity. And that is going to let us figure out what the displacement is from the curvature. And we can use the area and the average shear modulus to figure out what the shear displacement should be. Let's see. Okay, so we've got a displacement from bending, which goes like z to the 4, and not surprisingly, the shear displacement just goes like z squared, 2 more powers of z in the bending displacement. And let's see what V, we can maybe plot both of these, plot V and V shear from z is 0 to z, and see what we get. Oh, wait a minute. Z is 0 to L is what I meant to do. Okay. And let's see. So they're both bending down. That kind of makes sense. It looks like the shear displacement doesn't really start off at, well, it starts at 0, but we don't have, we have like a non-zero slope at that end. It is responsible for a fair bit of displacement by the time you get to the other end because this is a pretty wide beam there. So there's our bending and shear displacement calculation. To find out the total displacement at the tip, we'll just substitute z equals Lz into V plus V shear. And let's see what we get. Oh, I didn't call that Lz, I just called it L. So let's try again. And we've got negative 3.6 E minus 6, so negative 3.7 microns. This is a fair bit of force. It's sort of under its own weight. The bending that we're applying at the end is kind of on the same magnitude as the rest of the bending, so it's like double its weight in terms of the bending displacement, a little bit more than that if you look at the integral of this bending moment. You've got sort of like 3 times the total area of that due to this applied moment at the end. So maybe triple its own weight, but these are pretty strong materials, so they can support a fair bit of their own weight, and this deformation maybe sounds like it's about the right order of magnitude, a few microns of displacement after 1 meter of this beam under its own weight. I wouldn't want to have to hold this up at the other end here, but assuming the reaction at the wall can actually supply the forces to stop this from moving at all, then this seems kind of reasonable for the right order of magnitude for the tip displacement. All right, let's see if we can make this thing work in FlexPDE as well. So we'll make a new file here. Pure bending example 8424. Sure. And how do we do this? Well, we are going to need to do something new that we maybe haven't done in, I don't think we've done in FlexPDE before, which is make piecewise functions show up. So what we'll do is we'll say Lx is, you know what? How about we just say leave Lx and Ly out of this for now, and because we're going to have to draw this thing in the XY plane, Lz will still be 1 though. So there's going to be a lot new in this problem. Let's leave S applied out of this for now. What we'll say is that these parameters depend on y. So E is equal to, if y is less than 0, then 411 E9, else 70 E9. Okay. New is if y is less than 0, then 0.28, else 0.35. And G is still equal to this. We'll need to put in rho. Rho is equal to if y is less than 0, then 19250, else 2700. So this in FlexPDE, we could do it with an applied load on top, but we also have the ability to apply a weight directly by using this thing, using the density at different spots. We'll show you how to do that. So let's go and draw this. This is going to be different than before. So we're going to start off at 0, 0. Actually, that's probably a bad idea here. Let's take where's our picture of the cross section? There. So what do we have here? This is, what do we call it? We call this y bottom and y top. If we want this to be 0, 0, then what can we do? We can start at, maybe we'll call this, kind of thinking about letters we could use for this. This is sort of a width thing, so maybe we'll call this H. It's kind of this small one, and we'll call this thing B. I don't know that. Is that intuitive? Maybe. So let's suppose that we label this thing, and we'll label it H and B, right? And then this will be H, and this thing will be B. Okay, so in FlexPDE, the one that we're going to do here, we're going to say that this is our thickness H, and this is B, and this is H, and this is B. So using that, we can find some coordinates. Yeah, this one down here is going to be at, let's go with a smaller font there, and maybe a different color. And we'll say this one is at negative H over 2 in X and negative B in Y, right? And then what about at this corner? That would be positive H over 2, negative B. And we're going to go around the whole thing like this, right? So you see where this is going. Where are we going to draw this? How do we do this? Well, conveniently, all along the length, there's no load applied, so we don't need to worry about any of that. We can say start 0, 0. Well, actually, let's start at the bottom left corner here. Start negative h over 2 and negative b, and we'll define those things. H is equal to, what was it, 20 centimeters, and b is equal to 60 centimeters. So then we can map out this beam as follows. Start there, line 2, h over 2, negative b, 2 up there, which is going to be h over 2, 0. And then we're going to go to the right-hand corner here, which is a length of b over 2 out from the center. So that'll be b over 2, 0. Then we're going to go up by h to b over 2, h. And then over to the left side, which will be at negative b over 2 and h. And then drop down by h to y is 0 to negative b over 2 and 0. And then jump in to, what would that be, negative h over 2, 0. To, the line breaks don't matter in FlexPDE. We can just jump to the next line, no problem. To, where are we? Negative h over 2, 0. To, oh, we're done. To close. Right. Sure. And let's see. So does everything else work? We've got nothing applied yet. It's good to test as soon as you can. Yes. So this thing that we had in the code from a while ago, calculating volume change, no longer is necessary. So let's get rid of that. Haven't been using that for a while. And we don't need to make this contour plot on LX or report these values at LX points. We can go, what is the value of V at the tip, which will be 0, 0, and LZ. Okay, so what do? We have that it's blowing up because the end grid that was defaulting is too much, so let's stop specifying something there. And we have our good-looking T shape. Huzzah! Okay, so that's the first part. Now what we need to do is apply that bending moment on the end of this thing. So let's do that. Well, we have this thing in the notes that we figured out earlier that gets at the idea of how you could have a stress distribution that applies a pure bending moment. And we worked out that to apply a moment in Z, we needed an X stress distribution, which is like this. Well, now with X kind of pointing into the page, well, let's see, hold on a sec. What do we need? We need the moment at the end of this thing is making it bend down, which is a moment in the positive X direction. So from this thing's perspective, this is saying how much stress do you need to get a given out of the page moment MZ. We want an into the page moment of M end here. So that means we're actually going to want to set up, you know what, we can sort of work it out in the same thing here. We can say Sx is equal to how much, this is for a certain amount of out of the page moment, so how much into the page moment do we need? We're going to need, first let's figure out y bar. Y bar is equal to the same, it's a very similar integral that we use to figure out big Y bar, except we don't weight it with the Young's modulus, right? So what do we expect? This thing is going to be, oh, did we look at Y bar earlier? That was a missed opportunity. We should think about where that is. It should be pretty far into the tungsten, right? So it's negative 0.24. Yeah, it's almost at negative 0.3. And that should be lower down than actual y bar, the one that's just weighted by area, yeah, this is higher up because it's not as influenced by tungsten's superior Young's modulus like big y bar is. Okay, so that's little y bar, and now we should be able to say sigma x is equal to, well, this is how much out of the page moment, so if we want an into the page moment, then we'll say positive m end times y minus y bar over the integral of w times y minus y bar all squared from y is y bottom to y top. Okay, so this should be the stress that we need to apply on that face. It's higher at higher y values, which is indeed going to make it bend in the right direction, so we got the negative sign right. And if we haven't made any mistakes in this, and it's so easy to do, then we should have the bending moment applied correctly if we put this stress on the top Z surface. So how do we do that? This is actually not an SX, I should say. This is really SZ. It works out to be the Z stress that we would need for this setup. Okay, so let's check. How do we do this on that surface, by the way? It's here. You extrude it up here, but then in the actual boundary section, you say what you want if it's not going to be just load is equal to 0. So here we want a load in the W direction of this stress that we're applying. Here, we're going to say value of W equals 0, and value of U is 0, and value of V is 0. And this is going to be fixing it in all three dimensions, whereas at the end, we're going to apply this bending moment. So besides the end effects here, the anchor effects, we should get a displacement, which is from a pure bending setup. We can plot, make this plot a little bit better here. Rather than on x equals 0, let's plot the stress in Z on Z equals 0 and see what that looks like. Interesting. So most of the stress is taking place in the tungsten. That's because it's a lot stiffer. So you see a lot more of these contour lines are going through for this. The aluminum ends up with a very similar displacement and not much stress difference across this thing, like the changes that you have for a given step in the tungsten, because it's so much stiffer. So a little bit of strain difference here makes a lot more difference in stress than the strain difference here does. Okay, so that is something. Let's report we reported the value at the end, and what do we get for that? We got a value which is negative 1.85 E minus 6, and this is, if we haven't made any mistakes, just the displacement that applied moment should give by itself, not counting the density of this stuff, because we haven't incorporated that into FlexPDE yet. And this is about half of this total displacement. How could we compare that with what we're getting in Maple? Well, one way is to mess up the Maple simulation so that it is no longer including the weight. How do we do that? Well, we can set gravity to 0 and see how different it is. Okay, so it looks like using both shear and bending, we would have this. This is the tip displacement, right? Where was this? Subs, this. Okay, yeah, let's call it V tip, so it's a little bit easier to read. And we have 1.88 E minus 6. Well, that's pretty close. And as before, it should probably get even closer if we get rid of the Poisson's ratio coupling at that Z equals 0 surface. If we were to look at the other stresses on that surface, let's say contour of SX and SY on that surface, we should find that those are non-zero as well because we haven't freed that surface. We've got around the same magnitude as the axial stress in Z manifested as shear stresses in the X and Y directions on this face. So how do we deal with this? Well, we can get rid of it by freeing the surface in those directions. So on the bottom surface here, instead of saying value of U and V are set to 0, let's say, you know what, on that surface, you want to move in X and Y, you go for it. No more stress applied there. So now it's on the scale of E3 instead of E5. At least it's 100 times less. It's not quite no stress necessarily what it worked out. And how much displacement do we have? We have the problem that we need to reference this to the displacement at the start. So if we say value of V here minus the same value at 0, then we should have the actual displacement of this point, and it is closer to the one that we calculated there in Maple. All right, well, let's refix that surface and put in those things there, and now we're going to have the two same those two things being exactly the same answer in FlexPDE because there's no displacement at the 0, 0, 0 point because it's on the Z equals 0 surface, and we fixed that now. All right, now how do we go ahead and add in this gravity force? So Maple, remember we broke it to have a little g of 0. Now if we put that back, then we have more displacement, 3.68 E minus 6 meters. And we're not getting that in FlexPDE because we haven't incorporated the weight. We could find out the linear mass density and apply that on the top on the top surface of this thing as we did before, figuring out which one of these is the top. It looks like it is actually this one when we're at a y of h, and we're going from this point to that point. Change this to line 2. That doesn't make a difference. And then before this word line, we now can put in a boundary condition, which could be a stress in the negative y direction. But rather than do that, it's also possible to apply this directly as a change in as a force in the negative y direction here using the differential equation. You might remember from last week that those equations in FlexPDE are representations of the net force per unit volume. So in the direction of so if we want not the net force per unit volume on this thing if there is no gravity, but the net force if there is gravity, then what we would do is on the left, we'd have not just the derivatives of the stresses in the y direction, we would also have minus 9.81 times the density. And that's it. This now should incorporate the weight of this thing and give us closer to what we had in Maple when we have gravity applied. So that's all you have to do. Once you've put in what the density is, by remembering where the differential equations in FlexPDE came from, and not just this magic thing that you don't change anymore, you could actually go and mess with them a bit if you're feeling brave and willing to remember where these proofs came from, and say, all right, you know what, we can just apply the weight by saying this thing was the force per unit volume in the y direction, and if we now have a weight acting in negative y, we would just have negative 9.81 times the density, because that's the mass per unit volume, and so 9.81 times density would be the weight per unit volume. And there we go. We've got our conclusion and solved it in Flex, getting the same result, more or less, as we did in Maple. So when we did the Maple solution for this, because it was a cantilever and had that static determinacy without having to incorporate elasticity, we could do this using the previous statics approach, which is to say, first, the net force and net torque about the external body is 0, and then we found the support reaction. Then we found out we just wrote what the internal shear force and bending moment were as a function of position along the length of this. And then we could work out what the shear stress and deformation was and the curvature was by our elasticity relations from last week and this week to find out the total displacement. The beam equation method would also have worked for this, but with a little bit of a change from what we had before, because at the right end we had a fixed moment applied. So this means the boundary condition at the right-hand side is not the normal free end one where you say there's no moment applied. It's instead that the second derivative of displacement at the right end is not 0, but the moment we're applying at the end divided by EI. So we have to be careful about the sign that's showing up here. Why should it be negative the value of this moment that was applied at the end? The reason is because the second derivative, when we're saying that it's m over EI, this is talking about the kind of m that would make it bend upwards, right? This is an increasing direction, an increasing displacement in the y direction, and the moment here is making it bend downwards. So it ends up being v double prime at LZ is negative m over EI that you set at the end. And if you want to, you can rework out a lot of this same stuff using the beam equation. So what would actually be different about this? We'll just work out, let's take this thing and let's make it work it all out using the beam equation instead. So we still have mn applied, this P naught here, but we won't do this. This was the static stuff. And we won't do this or this yet. We'll do this later, maybe. We need y bar and EI, and then can't quite figure out C just yet, and we won't find V this way. Yeah, instead of all of that, here's what we're going to do. We've got y bar and EI, and then we're going to say desolve the fact that negative P naught is equal to, from the beam equation, EI times the fourth derivative of V flexure by, with respect to Z itself. So with respect to Z to the fourth. So here we go. We've got P naught is EI times diff of V at Z, V flexure meaning the bending one by itself, diff of V at Z with respect to Z 4 times. Then we've got some boundary conditions. So we have V at 0 is 0, D of V at 0 is 0. We have D2 of V at L, did I just call it L? Yeah, L is equal to negative M end over EI. And we have the third derivative at the end, because there's no shear force, is 0. So this should be giving us the solution to this system. Okay, so we won't be able to do this plot, and we won't be able to do this just yet, but the rest of it might work. Let's see. Oh, we need a comma. And we've got our V at Z solution. So let's say V is equal to the right-hand side of that. And then what's not figured out? Oh, we didn't figure out the shear force. So now that we've got this, how do we figure out the shear force of this? Well, we can say that the moment is equal to the, well, let's see, curvature would be the second derivative of V. So if we take derivative of V with respect to Z twice, and then we multiply that by EI, we should be able to get the moment, and then we should get the shear force by taking the derivative of that moment, and then the displacement for shear should work. Let's see. Oh, derivative with respect to Z. Yes. Okay, let's see if this does it? Do we have the same displacement as before? Looks pretty similar. Same tip displacement, now calculated using the beam equation instead of using the statics method that we had before. So with this little change in the boundary condition at the end, we can confirm this thing using the beam equation instead. All right, let's summarize what we talked about with Flexure. We found that bending moments in the z direction give a face a curvature, which is the moment related to the moment divided by the flexural rigidity. And to find flexural rigidity, we had to find out what a weighted average was, and specifically that y bar is the weighted average of y position weighted by the Young's modulus. Then you take the square of the difference of any point from that weighted average y position in y and multiply that by the Young's modulus, integrate that thing over the cross section, and that is your resistance to bending, your flexural rigidity. Now, if the beam has a constant bending moment throughout its length, like along its length, then it is said to be in pure bending. And this curvature is that happens locally from the bending moment is going to be the same all the way along the length and mean that it's just going to bend from a straight beam into a circular arc with a radius of rho, which is 1 over the curvature, and have an arc angle of phi is the length times this curvature by how arc length is defined. Length is the angle multiplied by the radius, so in other words, divided by the radius of curvature. Curvature is also the second derivative of the transverse displacement along the beam's length. If it has small transverse displacement, then that is just going to be the y direction for the setup that we have here, where we have a moment in z. But if the displacement is a lot, then this direction could change, and so you have to be careful using this formula. It's still going to be true locally, but when integrating across all along a whole length, you'll end up with some errors that can build up. For small deformation, a straight beam that has a downward distributed load P0 per unit length, you can solve for the displacement, the bending moment, and the shear force by solving the beam equation, which came from saying that the moment is related to curvature through flexural rigidity, and said the curvature is the second derivative of v with respect to length direction, x, and if you take this thing and you differentiate it, because the derivative of the moment should give you the shear force, and the shear force, the derivative of that should be the distributed load, because that's what's changing the shear force all along the length, then that leads you to this beam equation. This is a differential equation that you can solve as long as you have 4 boundary conditions, which you can get by looking at the ends of the beam. So by taking into account the fact that the shear force is equal to this times the third derivative, and the bending moment is this times the second derivative, and the angle is this, and the displacement is just the value itself, you can think about how joints work and come up with values that you know for each of these. So for instance, for a free end, if there isn't any force applied to it, then you know that the shear force, you know what the shear force and bending moment are, specifically that they're 0, and that's something that gives you 2 boundary conditions you can apply for a free end of a beam. For a pivot joint, on the other hand, you don't know what shear force it's applying, but you do know that it has no bending moment applied because it can't resist rotations about it. And you don't know what angle it's going to end up at, but you do know that the displacement is staying at 0. So this is an example of how you would use the boundary conditions and the beam equation to be able to solve for the displacement, and therefore the angle that it has at every point along the length, the internal moment, and the internal shear force. So the beam equation solves for the displacement from flexure alone, but to solve for the displacement from shear force as well, you need to take the flexure displacement it found and then figure out the shear force and use the shear stress relation that we had before and the shear strain, and then figure out the shear displacement. Now this can run into trouble if you end up having a breakdown in the requirements of this, notably the requirements that led to the shear force being calculable from only the displacement from bending, that saying that this is the bulk of the displacement, and we're going to meet the boundary conditions just with just with this, so that can run into a little bit of trouble sometimes if we have complicated boundary conditions that break this, especially if you end up with a setup where there's a lot of y in the x direction shear strain. This is assuming that that is 0 in order to say that all of gamma xy is manifested by shear strain on the x face in the y direction. So that's one big approximation that comes from using this to then calculate the total displacement, right? Remember, we can have these shear deformations that it really is depending on the displacement of the not just the x face in the y direction, but of the y face in the x direction. And you need both of those together, and we're ignoring one of them. So if you have a setup where that other one we're ignoring is non-zero due to the boundary conditions, if that's significant, then the shear deformation you're calculating using this is not going to be so accurate. Still, in the right kind of situation where you've got symmetry and can say that that shear deformation should be pretty small compared to the vertical one, then this can be a good correction to using just the bending displacement to figure out what the displacement should be. FlexPDE still likely will not agree with your answer because it's doing extra work that you're not doing in the Poisson's ratio coupling around the anchors. So around a fixed support or a pin support at the end, it's calculating what it really would do to the beam if it can't move in those lateral directions, and we're still ignoring that. We're ignoring the larger displacement stuff, and Flex is dealing with all of those things in a pretty good way, though it does have its problems of limited numeric precision, limited mesh density that makes it difficult to come up with a totally 100% accurate answer too. So each method kind of has its strengths, and by applying both of them, you can get further than with either one alone. Flex can deal with multi-layered beams by defining effective piecewise functions on the parameters like this. In computational multiphysics, we'll look at another way to do this, which gives us better numeric precision, but is a little bit harder to do. So for now, this is going to be a perfectly fine way to apply piecewise functions on material parameters. Now, it can only apply a pure moment to a surface by directly applying the stress that produced that pure moment, and this makes it a little bit tricky to know what stress to apply. Fortunately, we did some analytical work and figured out that we can apply a stress as follows to get a given moment that we're looking for. So just do some double checks if you're going to be using this for a different moment than a Z moment applied to an X surface. Then make sure that the moment that you're applying still is in the right direction. Just check that the stress that you get from the function makes sense to apply the moment that you're looking for. And that's it. Flexure is a big mega topic that is very relevant to a lot of different areas, not just buckling of beams in buildings and understanding how that's going to be operating, but also building microscopic force sensors and actuators for all kinds of different physical effects, energy harvesting things, all kinds of fun stuff with piezoelectrics. And we're going to return to this in a big way in computational multiphysics when we do exactly that. Thanks for watching, and I'll see you next time.